Okay, so today let us talk about multiple Compton scattering. Right, now I have already talked about this Compton scattering process many times. Let me just give you an example. Suppose we have got this 137 cesium source, and so this is your source, and from here what do we have? Predominantly, along with beta decay, we have predominant gamma emission having energy of 662 keV. Now suppose this enters. Now whenever I am drawing something like this, what I actually mean is the active volume of the detector. Normally a detector is made up of the actual detector where the interaction process takes place and we record it electronically, along with some enclosures, right? And those enclosures, they are required for the proper operation of the detector. Okay. Now, so all my diagrams, this means the active volume of the detector. So suppose this 662 keV gamma ray enters the detector. So what we are going to talk about? The three processes through which gamma ray can lose energy in this energy range: photoelectric, Compton scattering, pair production. Now look at the energy 662. So no pair production because this is less than 1022 keV threshold. Good. So only photoelectric effect and Compton scattering. Now suppose if this 662 keV is absorbed, then only we will get photoelectric effect. So let me just draw this. Suppose this is 662, right? Now this is your energy axis and this is counts. Then if this is number 1, this is number 2, and you are slowly observing. You have put a spectrometer in front of source and you are slowly observing the structure. What you see slowly is you see some count over here. Let me use some other color. After say 1 second, you see some count over here and some count over here, then over here, over here. So what will you infer? Tell me. See, this is 1 count, this is 2 count, this is 3 count, right? Now this is 662 keV, right? So this means that this entire region corresponds to complete energy deposition. And what about these cases? Suppose you observe something over here as well. So you see all these cases, they actually correspond to incomplete energy deposition. Why? Because 662, if it is fully absorbed in the medium, then it will be complete energy, and here lesser amount of energy is deposited in the medium. Now we already know that here Compton scattering is working. No pair production. Now if you take this spectra for say half an hour or so, then what you will observe is this. Okay, so you will observe something like this, and here is the 662 keV. Fine. So, and this corresponds to the full energy peak. Now when I am saying full energy peak, this means complete energy deposition. Now what are the possible ways of complete energy deposition? Let me give you an example. Suppose this 662 keV enters the detector and then it is completely absorbed by photoelectric effect. Then completely absorbed. One possibility. Another possibility, if this enters the detector, undergoes Compton scattering. So here Compton scattering 1, then it is absorbed by photoelectric effect. This is another possibility. Now there is another possibility. It enters the medium, it undergoes Compton scattering, say 1, again it undergoes Compton scattering 2, again it undergoes some other direction, Compton scattering 3, and then it is absorbed by photoelectric effect. So you see, I have shown here possibility 1, possibility 2 and 3 possibility. Actually there are so many possibilities. Okay. Now remember, there can be as many possibilities as possible. But if after all these possibilities energy is completely deposited, then we will have full energy deposition. Good. Now what about this hump? This, since there is no pair production, so this entire thing is due to Compton scattering. Okay. Now the nature of this hump, you can see the structure. It is actually given by Klein-Mishina formula. I am not writing down the entire structure of the cross section, but this is important whenever we are talking about electron or photon electron scatterings. Okay, so this is important during Compton scattering, Klein-Mishina formula. So this nature is given by this Klein-Mishina formula. Okay, so let me rub this part. So what I mean to say that anything which is, you see, this entire structure, this entire region, this corresponds to incomplete energy deposition. And this is Compton background. Okay. Yes. And this is complete energy deposition. And this is the full energy peak. Some part will be overlapped over here. Now the first thing is, why is there such a spread over here? So as I was telling previously, suppose you have got 10 rupees and you go to a sweet shop to order Rasagolla. One Rasagolla costs 5 rupees. So in 10 rupees you will get 2 Rasagolla. Always. It will not happen that he will give you 1 Rasagolla or 5 Rasagolla. Now if that happens, then there is something fishy going on. Okay. But whenever say a gamma ray enters and interacts with a detector medium, when I say detector I mean active volume, okay? What happens is that the number of charge carriers produced is never fixed. It varies, it fluctuates. Okay. Now this fluctuation is the reason for the energy resolution. In some detector you can have very sharp peak. In some detector you can have very blunt peak. Both have the same number of counts, something like that. So you will say, sir, this detector is good. Why? Because if there is some other peak nearby, you will be able to identify them. So we say good energy resolution. What will happen in this case? In this case, two will be overlapping and you will get a single peak like this. So you will not be able to identify that there are actually two peaks. Okay, but here you will be able to identify the two peaks. Why? Because the energy resolution is better over here. That means smaller. So in life sometimes smaller things, particularly here, are good because you are able to identify how many peaks are there. Now this case is a very isolated case, only one gamma ray. But in real experiments there are so many gamma rays because of so many nuclei which are de-exciting during a nuclear reaction. Okay, so fine. Now what I am going to talk about is the following. suppose I have got this 662 kV gamma ray. So what is the energy, maximum energy, which the gamma ray can deposit in the medium? Now, if you observe the Compton scattering, basic kinematics, then you will see that energy is known as Compton Edge, and the energy corresponding to this Compton Edge is given by 2 alpha E gamma divided by 1 plus 2 alpha, where E gamma is the incoming gamma ray energy, and this alpha is 511 keV. Now this gamma ray energy, if you write in keV, then this alpha, not 511, this is basically E gamma divided by 511, and E gamma is in keV. Okay, so if we have a 662 keV gamma ray, let's see what happens. So here we have got 662 keV. Okay, now what's the value of Compton Edge? That means, yeah, Compton Edge means, let me write it over here like this, E gamma and E gamma corresponding to Compton Edge. So first, if the energy is 662 keV, then what's the Compton Edge for this energy? You can calculate using this, and you will see that the value is 478 approximately keV. So this means that here somewhere, so this is 662, then this is approximately 360, and how much is this? Approximately your 330 plus 160, you can say. So this is approximately 490 kV approximately. So the Compton Edge, the first, this is the Compton Edge. Now, so 478 kV. What? So basically what is happening is the following. 662 kV enters the detector, and then it deposits how much? 478. That's the maximum possible. So if I ask you, is it possible to get 500 kV due to first Compton scattering? No. Let's see if it is possible or not. So what about second Compton scattering? So for doing the second Compton scattering, what will be the E gamma? The E gamma will be 662 minus 478. How much is this?
184.
184 kV. Now, what is the Compton Edge corresponding to 184?
77.
77. So you have all worked it out. Good. So 77 kV. Good. So this means that after this, 77 kV is absorbed. So how much energy is absorbed in the medium after this? Total energy deposited. Total energy deposited. First 478, first Compton scattering. Next 77, second Compton scattering, Compton Edge basically, plus 32. So what we will have to do here is the following. We have to do 184 minus 77. How much is this?
107.
107. 107. What is the Compton Edge? 32. Okay. So 32 kV. So the third one is 32 kV. This is after. Now remember, it is possible to have lower energy after third Compton scattering, but I am finding the maximum energy possible. That's why I am finding the Compton Edge, maximum energy due to Compton scattering. Okay. So how much does this sum up to? Let's go on. So after that, 107 minus 32. How much is this?
75.
Good. 75. What is the corresponding Compton Edge?
70.
17. Still not single digit. Okay. So here let me add 17. So this is after fourth Compton scattering. This is the fourth. Next, how much is the? So we will do 75 minus 17. How much is this?
59.
How much is the corresponding Compton Edge?
11.
11. So this is 11 after fifth Compton scattering. So let me add this up. How much is this? So after 5 successive Compton scatterings, so this is 1, 2, 3, 4, 5. Maximum energy deposited. Add this up. How much is this?
614.
Good. So this is 614. We have crossed the 600 mark. So if I ask you in the examination, given the incident energy is 662 kV, after how many successive Compton scatterings can we have 612 kV? So the answer will be minimum 5. Okay? I am calculating the maximum possible. Now it is possible that the gamma ray undergoes 6 Compton scattering, but it doesn't correspond to the Compton edge for maybe 2 of them. So the energy deposited will be lower. So minimum 5th scattering. Understand? So this is more or less overall scenario. So let me add up. So this one is 478 over here. How much is the next? Add these two. 555. So this is after first Compton scattering. Okay. Next, how much? 555. Somewhere over here. Second Compton edge. After that, add these 3. Approximately 590.
7.
Okay, so and so on and so forth. It will go closer and closer. Okay, so remember the graph I showed you. So the graph basically looks like this. This is the stuff. Okay, so this is the region. You see, this is the region for multiple Compton scattering. As we have also checked through the calculations. So this corresponds to the first Compton edge, and then we have got this multiple Compton, this region. This is finite because of this multiple Compton scattering. Okay? Good. So what Siddhant is asking me is, if this is the actual structure. Now sir, you already showed us that this is first and this is the second, this is the third, this is the fourth, corresponding to Compton edges, right? So what he is asking me is, why are there counts here? Why are there counts here? Why are there counts here? The answer is very simple. Consider this full energy peak. Do you see a Dirac delta function? Do you see a very strong pike? No. Why? Because of energy straggling, which causes the detectors to have energy resolution. The same thing will happen here as well. During all these processes, remember, you can think of energy deposition process as there is some error involved during the number of charge carriers produced. Now, how many processes are having here? Here there is 1, 2, 3, 4. Now each time the process will go on, more and more uncertainties will add. Okay? So there will be, this is the reason for that. The errors will add up, or the uncertainties in the number of created charge pairs will add up. And as a result, you get this smooth structure. Good point.